Students? Yes, okay. Good afternoon once again, students. So we are going to start very important discussion, and we are going to see the definition, formula, and very important in the joint probability distribution unit. A very important topic, that is Markova chain and stochastic process. Please remember this. It's a very important chain, and we see how this process has been done in examples. We are going to come across this, and we can see a very good application in the Markova chain and stochastic process. We'll just go one by one. Markova chain. It is a Markova process in which the state space I is discrete. I think you have come across what is discrete. It is finite and countable. Thus, a Markova chain is a finite stochastic process consisting of a sequence of trial whose outcomes, we are going to take this as outcomes as x1, x2. So they are going to we are going to consider this as outcomes. So they are finite. Please remember this. In Markova chain, there are two conditions. This is very important in the to solve the example especially. So I is nothing but we are going to take a1, a2 till am, which are finite set of outcomes. Second condition, outcomes of any trial depends at most upon the outcomes of the immediate proceeding trials and not upon any other previous outcomes. So please remember this. Suppose if I take the numbers as our outcomes, that is 1 2 3, if I take, so one will be depend, two will be depend on one, and three will be depend on two. So like this we are going to have the proceeding student. Suppose another example, if I take 1 3 8 10, so this is not our, it doesn't satisfies the Markova chain. So please remember these two condition to simplify the examples, it will be helpful. Next we see the Markova property can be stated as, that is probability p xn is equal to in, such that x naught is equal to I naught, x1 is equal to I1, like this it will go and continue. And you can see this is equal to the probability xn is equal to in, such that xn minus 1 is equal to in minus 1. So means whatever the random variables are we going to consider, the corresponding values, that is outcomes, you are going to calculate in Markova property. Now the system is said to be in the state of AI at the time n, or at the nth step if AI is the outcome on the nth trial associated with each order pair of state AI aj. The number Pij gives the probability that the system changes from ith state to the jth state. Means what this means, students, whatever this Markova property is there, that is probability of xn is equal to I, and this system is there, we are going to start from AI and then it will reach to aj. So the number they have given for this probability, we are going to get the Pij as the matrix. So we just see there. In other words, Pij is the probability that aj occurs immediately after AI occur. That is what I say, that is the preceding, it depends on the preceding values, we are going to get the next value. So the number Pij are known as transition probability. So we'll just see what is transition probability is. Yes, first we'll go see, it is a transition matrix. So remember here, I'm going to take the square matrix P of transition probabilities, that is a Markova chain we are going to calculate actually. So this is Pij, so this is our matrix, students. Okay, then for this transition matrix, we can also calculate probability vectors. Suppose the outcomes are vectors, probability vectors are there. So here what probability vector says, V is equal to V1, V2 till Vn if Vi is greater than equal to 0, students. So please remember, vector will be equal to 0 or greater than 0. It will never be negative. This is also helpful for the solving the example. And sum of all these vectors, so whatever the vectors you are going to take, if you add this, all vector will be always equal to 1. If this two conditions satisfies, then we say it is nothing but probability vector, or it is a transition matrix what we going to calculate. So what you are going to remember, I have just made some note here. A vector whose components are non-negative, yes, it must be positive. Positive means non-negative, but their sum is not 1, can be converted into probability vector by dividing each component by the sum of the components. So this is what very important note they have given here. Suppose I have taken one example. These are the vectors. Okay, they are positive. The values are positive. They are going to take the vector. But your sum is not equal to 1. Yes. If you add 3 plus 0 plus 2 plus 5 plus 3, it is not equal to 1. So how you can make this as probability vector? Very simple. Add these values first. 3 plus 0 plus 2 plus 5 plus 3. So what is this equal to, Raj? Please tell me. To add this value, you must get this as 13. This, yes,
13.
very
Sir,
good.
1-3.
Yes, 1, 3, very good. So how you are going to convert these vectors into probability vectors? Take this 13. Now divide each component by 13. Means how will be your product now? Probability vector 3 divided by 13. Okay. This is 0, keep 0 as it is. This is 2 divided by 13. Then this is 5 divided by 13. Okay, next again it is 3 divided by 13, students. So this vector will give, this example will give you, that is probability vector. So how to convert vector into probability vector we have understood. Next property, what it says, negative value is not probability vector. Suppose the example they have given 1 upon 4, 3 upon 2, minus 1 upon. So minus, if it comes, we not consider this as probability vector. It is not probability vector. Suppose next I have taken next point, that is sum of the component must be added up to 1. So please add this value 1 upon, in this example you can see 1 upon 12 plus 1 upon 2 plus 1 upon 3 plus 0 plus 1 upon 4. If you add this value, is it equal to 1? Yes, you can see if you add this value, this will give you equal to 1, student. So first condition satisfies. What is that? If the vectors they have given is positive. Second condition satisfies. If you add all the vectors, it is equal to 1. Means this vector, that is this example, is a probability vector. Okay. Next we'll go with the stochastic matrix. So you can see now I'm going to take here P is a square matrix with each row being a probability vector. Means each row is probability vector here, students. So please remember this. In other words, all the entries of P are non-negative. First condition. Okay, it must condition, first condition must satisfy. Whatever the matrix I'm going to, square matrix I'm going to take, all the entries must be non-negative, and sum of the entries of any row is equal to 1. This is what the condition satisfies. Then we say this is stochastic matrix. So the just name they have given, peculiar name they have given here, just to identify, differentiate from normal matrix to stochastic matrix. So next you can see here again, note I have taken, simple. So a vector V is said to be a fixed vector or a fixed point of a matrix A if V into A is equal to 0. So what I have done here, I have taken here vector V and there is a matrix A. If you multiply them, then this must be equal to 0. Remember here, vector must not be equal to 0 because you are multiplying to the matrix, and this will be equal to 0. This we can do. This is one of the property. Similarly, another property I have taken K. K is some constant. Multiply this K to the V, that is vector. You can do that. Suppose if you take a constant K as 2, then you can multiply 2 to all the vectors similarly. Okay, it satisfies the condition. Similarly, again, a very important point, it is also useful to solve the example, that is regular stochastic matrix is always positive. Remember this. So when you multiply and get the answer, whatever the answer you are going to get, it must be also positive only. Then we take this as regular stochastic matrix. Okay. Next note will come across, that is the yes. transition matrix, whatever we have taken P as a transition matrix of a Markova chain, is a stochastic matrix itself, student. So remember, so what it says, there is a transition matrix, okay, of Markova chain. If this condition satisfies, then the same matrix we are going to consider it as stochastic matrix, student. This will be easily understood using the examples. If you go through the example, you can see this matrix, okay. So now we'll see first example, example 1. Which vector are probability vector, student? Yes, start solving the example here. You tell me which vector is a probability vector. Is vector 1 probability vector? Yes, please tell me. Yes, it must satisfy two conditions. First, all the values, whatever the vectors are there, they must be positive. Here you can see it is one value is negative. So here negative value is there, means negative vector is there, therefore it is not probability vector. Why it is not probability vector, student? Because negative vector is there, minus 1 upon 4. You can see here it is minus 1 upon 4. Therefore we take this as not probability vector. Similarly, go for the second one. Yes, please try yourself. Second one, can you try? First condition satisfies that all the values are positive. Yes, very good. All the values are positive. Now go for second value. If you add all these values, is it equal to 1? Yes, please check this value. It is 5 plus 5 divided by 2 plus 0 plus 8 upon 3 plus 1 upon 6 plus 1 upon 6. Is it equal to 1? Yes?
No.
It is not equal to 1, means this vector is not equal to 1. Therefore, it is also not probability vector. So this is also not probability vector. Okay, no problem. We'll go with the third one now. Now just check now. These are positive. Okay, first condition satisfies 1 upon 12, 1 upon 2, 1 upon 6, 1 upon 6, 0, 1 upon 4 is positive. Okay, it is done. Go for second property. Add all this 1 upon 12 plus 1 upon 2 plus 1 upon 6 plus 0 plus 1 upon 4. Is it equal to 1? Please check. Is it equal to 1, students? Yes, please check. Is it equal to 1?
Yes, sir.
Very good. Means this vector is probability vector. So this is how you have to identify. Very good. Okay. Now in the next example, you can see 3, 0, 2, 5, 3. So already we have done this note. I think whatever the example they have given, they are the vector, they are positive. If the components are positive, then what we do, add this components, so totally it will be 13. Then 3 upon 13, 0 we get, 2 upon 13, 5 upon 13, 3 upon 13 we get. Okay, this we have done the process. So now what we are going to check now, is this positive? Yes, it is positive. Okay, second condition, is it equal to 1? Please check. Is it equal to 1, students? 3 upon 13 plus 0 plus 2 upon 13 plus 5 upon 13 plus 3 upon 13. Is it equal to 1?
Yes, sir.
Yes. If it is
Yes,
equal
sir.
to 1, means done. It is also what we get here. It is probability vector. This is how we have to identify the probability vector. So this is just a simple example it is. Now we will go with the second question. Very, very important. So see here, very, very important. Once again, I will inform you that don't miss this example, because this is will give you all the idea of the next example. Now you can see in this example, they have given figure. Okay, I have seen the figure. You can also see this shows 4 compartments with door leading from one to another. Yes, there are compartments and there are doors. A mouse in any compartment is like equally likely to pass through each of the doors of the compartment. Find the transition matrix of the Markova chain. Draw the transition diagram. Yes, very, very important, student. In the exam, in the final exam also, in the joint probability distribution unit, please remember this one question will be there. Not this means particular, not, they will change some values, but such questions will be there like Markova chain, stochastic process, and then you have to draw the transition diagram. It's a fixed question for the final exam. Remember, find the transition matrix they will ask of the Markova chain, and then you must also draw the transition diagram. So very, very important for the final exam. Suppose here they have given the mouse. See how, yes, what we say, a mouse is very mysterious. Yes, what he is doing, what this mouse is doing, from one compartment it is going to another compartment. So you can see there are 4 compartments. So how we are going to solve this? We're going to take the transition matrix. So this, if you understand this transition matrix in Markova chain finish, you understood this topic only. Yes, now see. So first what I will do here now, I will fix this mouse. I don't know why this pen is writing anywhere. Okay, so I'll fix this mouse. I'm going to take this mouse in the first compartment. Okay, so now you can see from the first compartment to the first compartment, how many possibilities are there? 0. Tell me why? Because it is already there in the first compartment. Again, how it can go to the first compartment? So therefore the possibility are 0. Probability will become 0, student. Now, how many total number of ways to go outside the first compartment? See, 1, 2, 3 ways are there. Total number are 3. Now, from 1 to 2, how many ways are there? 2 ways are there. And what is the probability you are going to get, student? Divided by total number of ways. So 2 ways from 1 to 2, and total number of ways are 3. So this is our probability. Okay. Next, from 1 to 3, suppose the mouse is going to travel from first compartment to the third compartment. No, there is no way. So we are going to get here 0. Similarly, the mouse is there in the first compartment. It is now going to travel to the fourth compartment like this. Okay. How many ways? Only one way is there. Okay. So here it is only one way is there. Fine. So what is the probability here?
Sir, can you repeat? Sir, can you repeat?
Yes. I will repeat. Okay. What I am trying to do here is I am going to find the probability, right? Probability vector. Okay. So this, in this transition matrix, mouse is in the first compartment. Okay, please remember, mouse is in the first compartment. How many ways are there to go outside this compartment? 3 ways. 1, 2, 3. This you have understood. Okay. Now what I am saying is, from this mouse is going to travel all the compartments. Let us see from first only. So mouse is there in the first compartment, and how it can go to the first compartment? So probability will become 0. So I have taken here 0 probability. Now mouse will going to travel from 1 to 2. Okay. So how many ways are there? 2 ways are there. 1, and this is 2 ways are there. Okay. 2 way are there. But what is the total number of way? 3. So what is the probability? 2 divided by 3. So please remember this. Next, from 1 to 3, there is no way to go. Yes, it cannot go directly. It cannot jump the building and go, right? So there is no way, therefore the probability will become 0. Okay. Now mouse is in the first compartment. So it is going, now it is going to travel from first compartment to the fourth compartment. So now you can see how many ways are there here. Only one way to go from 1 to 4. So 1 divided by how many total number of ways are 3. So probability will become 1 upon 3, students. So please remember like this. So how the mouse is going to travel from first compartment to all the compartments. We are going to take this as the probability matrix, that is P is equal to, so because there are 4 compartments, therefore the matrix will be of 4 rows, 4 columns. Okay, and from the first compartment you have seen, first compartment to first compartment it is 0, first compartment to second compartment probability is 2 upon 3, from first compartment to the third compartment it is 0, from first compartment to the fourth compartment probability is 1 upon 3, students. Now okay, now we'll go to the, yes, now we'll go to the second compartment. Suppose the mouse is in the second compartment, that is 2. So from 2 to 1 again. So first we'll see how many ways are there. Total number of ways are 1, 2, 3 ways are there. 3 total number of ways are there. But from 2 to 1, yes, from 2 to 1, how many ways it is going to travel? 2 ways. So what is the probability? 2 divided by 3, students. Okay. Now 2 to 2. Yes. Now mouse is going to travel from second compartment to the second compartment. How it is possible? It is not possible. Therefore, probability is 0. Okay. Now mouse is going to travel from 2 to 3. Only one way is there. And total number of ways were 3. So 1 divided by 3. Now next again, from mouse is in the second compartment. From second compartment to the fourth compartment. How many ways it is going to go? There is no way. Therefore, we are going to consider this is 0. Therefore, what we get here, students, the probability from 2 to second compartment to the first compartment is 2 upon 3, and second compartment to second compartment it is 0. Second compartment to third compartment is probability is 1 upon 3, and from second compartment to the fourth compartment it is 0. So please remember. Now next, okay, now the mouse is in the third compartment. Fine. So what is the total number of ways to go outside this compartment? First we'll see. That is 1 way and 2 way. Only 2 ways are there. Okay. Please remember, total number of compartments to go outside. Total number of ways to go outside this compartment is 2. Now we'll see one by one. From third compartment to one compartment. Okay. There is no way. So probability will become 0. Okay. From 3 to 2. How many ways are there, students? Only one way is there. Therefore, 1 upon 2. Total number is 2 ways are there. From 2 ways, only one way is there to go to third compartment to second compartment. Okay, 3 to 3. I think you must tell me the answer now. 3 to 3 compartment, can you tell me? Yes, Gaurav?
0.
Yes, it is 0. Very good. I'm going to take here. This is 0. Okay, this is 0. Similarly, what will be the fourth now? It is 1 upon 2, because only one way is there. So 1 divided by total number of ways to go outside, it is 2. So next, now mouse is there in the fourth compartment. Okay. So first you have to tell me what are the total number of ways to go outside. It is 1 way here, and here it is 2 ways are there. I think the screen is clear. Yes, is it visible? Screen is visible, students? Okay, so there are total number are 2 ways. Okay, now we'll start one by one. From 4 to 1, the mouse is going to travel from 4 to 1. How many ways are there? 1 way is there only, and divided by total number of ways 2. Okay, next I'm going to take here 1 upon 2. Similarly, from 4 to 2, there is no way to go. So probability vector will become 0. Here we are going to get 0. Similarly, now go for 4 to 3. The mouse is going to travel from 4 to fourth compartment to the third compartment. So there is only one way to go outside. So total number of ways to go outside is 2. But to go for third compartment only it is 1. Therefore, probability will become 1 upon 2. Next, fourth compartment to the fourth compartment it is 0, because it is already there in the fourth compartment. how it is going to travel from fourth compartment to fourth compartment. So there is no probability. So therefore it is 0. Now we can see this matrix as the transition matrix, and whatever this chain, we can see this mouse is traveling from first compartment to second compartment, third compartment, fourth compartment. Whatever this chain you can see there, it is known as the Markova chain. So now we are going to draw the transition diagram. So after finding the matrix, very simple it is. Now we see the diagram, very important, student. Now you can see here we are going to draw the transition diagram. First I will fix the values. I'm going to take a1. Yes, they are the outcomes. I'm going to take here now a1, a2, yes, a3. I'm going to fix this as the compartments. I can see from 1 to 2, you can go through the matrix, it is very easy. From 1 to 1, it is 0. Okay, there is no chain. From 1 to 2, you can see it is 1 to 2 is there. Yes, it will travel from 1 to 2. Mouse is traveling from 1 to 2. What is the probability? 2 upon 3. You can see in the matrix, it is 2 upon 3, students. Now from again 1 to 3, it is 0. So no need of going 1 to 3. I will go for 1 to 4. Yes, it is going to travel. Mouse is going to travel from 1 to 4. The probability here is 1 upon 3. Okay. Now next we'll go to the 2. Okay. In the 2, we can see second compartment to the first compartment. Yes, mouse is going to travel. And what is the probability here, students? It is 2 upon 3. From 2 to 2, it is 0. Okay. From 2 to 3, you can see it is probability 1 upon 3, students. Now 2 to 4 is 0. Okay. It is not going to travel from 2 to 4. Next, go for 3. A3. That is the third compartment. Mouse is in the third compartment. 3 to 3 is 0. 3 to 2. So mouse is going to travel from 3 to 2. Probability here we have, it is 1 divided by 2. Okay. So again from 3 to 3 it is again 0, students. Okay. No, not to worry. So again this mouse is going to travel from now 3 to 4. So you can just see 3 to 4 it is going to travel. What is the probability? 1 upon 2. Here you can see in the matrix it is 1 upon 2. Next, go for fourth one now. Fourth one, mouse is in the fourth compartment. In the fourth compartment to the first compartment, yes. First compartment probability is 1 upon 2. From 4 to 2 is 0. And then from 4 to 3 is, again it is 1 upon 2. So like this, you should draw neatly, and then you will get the diagram like this. Is it clear, students? So this is what we get the, if you draw neatly, you must get this diagram. So this is known as transition diagram. Please remember this. So very important example this is, students. Go through this video once again. If you have any doubt, please ask me. Yes. Thank you, students.
Sir,